There are all kinds of people thinking about all kinds of things all of the time. That sentence sums up what I would describe as the ultimate deterrent to oppose the urge to invent. It is the feeling that it's all been done. Someone must have done this. I was born too late. All the good pickings were in the last century. And other such rubbish. Isaac Newton was right when he declared, "If I can see further than others, it is because I stand on the shoulders of giants." And you start counting up Newton's giants. You say, right, Leonardo da Vinci, Galileo, Archimedes. You soon run out of ideas. But Newton knew nothing of Faraday even, Maxwell, Rutherford, Max Planck, Niels Bohr, Geiger, Einstein, Mach. Our list of giants runs into hundreds. So the opportunities for new inventions and discoveries were never greater than they are today. And of one thing we can be sure, they will be even greater next year. Now, last time I left a bit of unfinished business about the magnetic river, which we didn't squeeze in, so I propose to do that now. It will illustrate for you how inventions take place. It is often the pressure of something else, like Transpo 72, or a chance remark, and I make most of my inventions when I'm talking to other people. They've come to see me about something or other, we get to talking about something else, I drag them from their interest into mine, and then they thank me when they leave, and I feel as if I should pay them a fee because I feel as if I've used their brain to sort of reflect from. Now, when you discover something or observe something for the first time, you think, God, what about that? I wonder how that works, you know. And then you make one, and you look at it, and you decide you better find out how it works. And so you set about a detailed series of experiments, and eventually, of course, you have to do the sums. It wouldn't be respectable without doing the sums. And so you do the sums, and then you publish it as a paper in a learned society journal. And when you do this, you write it as if it were done from the front, as if on morning one you said, I will now invent a magnetic river. You see, and where you go, and you do the sums, and this very unfortunate phrase keeps coming in. Now it is clear that, and clearly, obviously, sort of, none of it's obvious. It wasn't the day before you started. No, you do it from the back. First, we made a magnetic river for Transpo 72, and then I asked one of my postgraduate students, Alan Atwood, if he'd make me a machine that would sort of simplify it down so that we might understand what we were doing. And he came up with this machine with just 3 of the long row of cores that you saw last time, and there was some question about how the width of the aluminium sheet would affect the stability. So you begin with a very small voltage, so you can just lift it off and it's stable. Then you try a wider plate at the same voltage. That's all right. It's a little bit skewed, but that may be a defect in the apparatus. Now you must remember that at this time a commercial company was making the Transpo 72 model, and they realized that it was much more difficult than flying an aeroplane. In addition to pitch and roll and yaw, you've got lateral disturbance, vertical bounce, and propulsion to look after as well. You want stability in 5 axes and propulsion in the 6th, and you'd like to get critical damping. Now, the first vehicle they made went along the track all right, but once it was disturbed in roll, it rolled all the way. It was hardly damped at all. And they discovered that if they made the plate wider, then it damped out the roll, And I said to them, but I bet it makes it less stable. And they said, oh yes, it's not as good in lateral shift. I mean, this one's quite good. You can move it quite a long way. So you try a bigger one. That's higher still. That's gone really skewed. And it's a little bit more shaky on its legs in that direction. And you put a very big one on, and it falls off either side. So I went armed with this information to see the firm and said, look, you're losing stability by doing that, and you've got to go higher yet. And a thing which is stable, just, that sort of thing, when you try and raise it to 2 inches, of course, it'll go totally unstable. I said, look, I'll show you. We start with the one which is unstable. That is not going to stay there, it falls off. Would you just like to hang on to it, Bill? What I hadn't realised was you should take your courage in both hands, never mind winding the current down, you should wind it up. That is one of many reversals I've had to make in my inventing. You think you're going along the right path, and all of a sudden it gets darker ahead, and all the time you should have been going the other way. Who would have known that you had to raise the plate, increase the current to make it more stable? Well, now we then saw the magnetic springs, and I thought I'd like to show you the forerunner of the magnetic spring experiment, because it does display something new. This is a pendulum in which the sheet of aluminium has been replaced by a piece of steel with some copper wire wrapped round it and joined. Now, I can switch this on and start. I pulled a wire. I thought I felt something give. Yeah, thank you, Mary. Turn that down. I can think of a good 3 reasons why that pendulum should not begin absolutely from rest. But I'm going to switch it on and then hold it in the most steady position I can find, and you'll see if you have the patience, start from absolute rest, that doesn't look as if it's going to oscillate, does it? And even if it begins a little oscillation, you suspect that's only some defect in the structure. You can't see how that could go on building up higher and higher and higher. You've got your 2 linear motors that were on an arc, back to back. When it reaches the end of the travel, it hits some real springs, not magnetic ones, and then it runs rather smoother. So there's a magnetic spring plus mechanical spring. Now this is an old chestnut with modern modifications. I didn't show these in 1966. First of all, it is the ordinary jumping ring experiment that began in 1880. It still fascinates people. You put the ring back, it appears to float. You can go on arguing about where this should float, which is only half as thick, and you might come to the conclusion it should float in the same place, and you try it, and it does, and so it isn't very interesting. And this is where the invention part comes in. If you're not an inventor, you say, yes, it should float in the same place, and you try it, and it does, and so you put the apparatus away and you go home. But if you're an engineer, and you're a curious engineer, you say, I'll make it thinner still. It's down a little. Right, make it thinner still. Ooh, it's down a lot. Now, why is that? And you start to work out reasons why this is until you're convinced that you know why this is too thin. If I put a thinner one on still, of course it'll not have any lifting force at all. Or will it? What do you think? You think it will? Well, you're wrong, it doesn't. This is a bit of household kitchen foil. Just shows the beginnings of lift. And I was satisfied that I hadn't understood this until one night I've been showing someone and left this thing switched on. As I usually did, I collected the rings together and sort of put them over the top. As I was doing it, I noticed something happened. And immediately you've got a new world, you've got a new white rabbit to follow, you've got a new curiosity. Look at that. Now you can't tell me that the current in this poultry ring is attracting the current in that poultry ring, because it isn't. It's this one that's shoving this up. So why didn't it shove it before? I've not really been able to exploit this yet. All I know is it's got possibilities, because our normal idea of loading something is to put more weight on it, like loading a camel, and they say the last straw breaks its back. But in this case, the more straws you put on, and the higher it lifts. This thing gets better as it gets more weight on it. Look. You can go on loading it and loading it until you've used up all your small ones, and you start on the thicker ones, comes up a bit more, and you start on your thicker one again, comes up some more. The bigger the better. Now, can we lose this one now? Ready? Other side. Oh, yes, not that side. Thank you. The liquid. Ah, some cooking perhaps. No, something more earthy than cooking. Writing with printer's ink. That's not printer's ink. It's too thin for printer's ink. It's got the viscosity of water. It is in fact kerosene with certain additives, but as you see, it behaves in every way like a normal liquid. It has a rather curious smell, but it's just a liquid for the moment. This, by the way, is made of porcelain. This is an aluminium sheet, nor is there an aluminium sheet embedded in it. What's he going to do with that? He's going to get himself a great big magnet, and he's going to hold a plate of liquid over the magnet. A heap of liquid. No less. And a large attractive force holding it down. Take away the big magnet and we'll do it with some alternating current magnets. We'll try it on Allen's levitator. You've got to watch it doesn't crawl over the side, because if it crawls over the side, it makes a dreadful mess of everything. All right, it should be on. It's having a try up that other side, Bill. Now, those are virtually only single-phase fields. Now we're going to try putting at least a moving field on by using our ball floating coil and shading it, as we call it, with a piece of aluminium to produce a travelling field. You now carefully place the plate on there. We'll switch on again. Where are we? Here. Whoa! It's like a cauldron boiling. What's more, it's dividing up into walls. We've seen that before with iron filings. This is really only an extension of the iron filings game. It shows you the best natural position for travelling magnetic fields as far as the magnetic circuit's concerned. This is magnetic liquid. What shall we be doing in a year's time? Well, one of the things I hope is that we shall be able to make particulate smokes of this material and then have not a magnetic gas but at least a magnetic smoke, and then we can really see fields in 3 dimensions. This is a tremendous tool in the hands of the research worker. Thank you, Bill. Shut up. Now, even though no two people are exactly alike, there are ways of classifying you not only by whether you're left or right-handed, or by race or religion or age, but by your outlook. And just as every man, and I hasten to add, as opposed to every woman, is a better driver in his own opinion than all the other idiots they allow on the road, so every man and every woman is a potential Thomas Edison or Marie Curie. Never notice a second Einstein. Always the discoverer, the inventor. Now, it is said of people in the army that every private soldier carries a field marshal's baton in his knapsack. So I can tell you with every confidence that each of you, at one time or another, has had a quite original thought. And this is the result of your unique combination of inheritance from your parents and subsequent experience, which is what we call you. Now, mostly these new thoughts have passed unheeded, because inwardly you felt that your thoughts couldn't really be of all that much importance, not earth-shattering. It is as you grow older that you begin to take yourself more seriously, and taking yourself seriously is very bad. It means that you spend the autumn of your life when you retire in writing to professors like myself, who have more than plenty to do, telling them about, those unfortunate professors that is, telling them about the world beaters that you've invented, and a very common species of world beater that I have literally hundreds of letters about is an electric motor that drives a generator, and you use some of the output from the generator to drive the motor. And then you've got all the rest spare for solving the world's energy crisis. Now, I don't want any more of those, please. But although that seems ridiculous, it is surprisingly easy to pull the wool over your eyes, especially in some of these mathematical proofs that naught is equal to 1. Were we going to do this next one, I think? Yes, we were. I'm very fond of this geometrical proof because you can do it without actually ever saying anything which is wrong. You take a square, you draw a square, and then imagine you'd got compasses, and you place compass point on this corner, and you make the compasses the length of the side, and you strike an arc down there like that. I'll draw this next line in a different colour to make the diagram clear. That is an arc. Now, since that point is now lower than the top of the square, I can join it by a line which must obviously slope downwards. And the middle point of that line will be to the right of the middle point of the top side of the square. So if I bisect that longer line at right angles, it comes down there. And if I then bisect the sides of the square, the vertical line, that vertical line will cut the horizontal, the other line. It must do, because that was no longer bisecting a horizontal line. And the rest is just drawing lines. You join from this corner to the point of intersection, you join from this corner to the point of intersection, and you join from this corner to the point of intersection, and from there. And we're going to consider, I'll draw that line in red, we're going to consider those two triangles. They don't look much the same, but that's just my rotten drawing. Now, let us consider what is equal to what. Well, that's the side of a square, that side of the triangle. It's equal to that side of the square, which is, of course, equal to that side, because those are two radii of a circle. And then this line is the same length as that, because they are a pair of triangles, result of perpendicular bisection. So that equals that. And similarly, these two longer lines are a result of bisecting at right angles, that base, and so you've got that line equal to that line. So you now have two triangles which are three sides equal, so are congruent even though they don't look it, and among other things, this angle is equal to this angle. Now this angle is made up of 90 degrees plus, shall we say, angle A, which is that. Well, since that angle A is the same as this angle A, because they were congruent triangles at the bottom, then this other angle is 90 degrees plus A plus this angle B. And subtracting, naught equals B. Well, if you haven't seen it before, it might worry you for a little while. The fact is, remember, I said I didn't say anything that was wrong. I did something that was wrong, but I didn't say anything wrong. Now, it would be equally disquieting, however, if, having sort of put off the would-be inventors of perpetual motion, if as a result of what I'm now saying, none of our elder citizens with a mountain of experience of life behind them were to dissent from writing to me about an idea that they've been tossing around for years and never had opportunity to get a second opinion. Take a case in point. It is now nearly 2 years ago that I was telephoned by a man called Alexander Charles Jones. who asked me if he might bring me a box of apparatus which he said, when put on frictionless casters and set in motion inside, would displace itself outside its own dimension. Immediately I knew this man was different. Any ordinary crank would have said, Alec's not a crank, it's only others who say he is. No, I should have said any ordinary crank would have said, how would you like to see Newton's laws disobeyed, you see? But Alec said, outside its own dimension. So he knew already the old chestnut, if you put a ball of lead in a box and a spring behind it and you compress it against this side of the box, and then when you release it, more or less the lead stays where it is and the box does that. And you say, oh look, action without reaction. But of course the centre of mass has stayed the same. But he said it will displace itself outside its own dimensions. So I said, does your box contain anything that might loosely be described as a gyroscope? And he said, in the box there is a gyroscope. I said, I think you'd better come and show it to me. Why did you say that? Why the question? I said, well, because I know enough about gyros to know that they're like electromagnetism. And I've studied electromagnetism for 30 years, and I know darn well I don't understand it. And I don't understand gyros either, but I can invent new things in electromagnetism once a year. And if you've got something new about gyroscopes, I want to see it. And he brought it, and it did. And that was the start of a new line of research for me. And then, about a year later, I met a second enthusiast called Edwin Rickman, who added his own brand of instinct that improved the ideas we'd already got. Let me say of Alex Jones that since I first met him, I've been convinced of both of the validity of his argument and been impressed with his feel for what I'd call the elements of nature, a thing that the more learned, acknowledged men of science and mathematics have seldom had, a natural feel for what goes on. And combined with the Rickman idea, I may say that neither of these gentlemen can be described as elder citizens, unless you describe me as one, because they're the same age as I am. So there is the first message for all of you as potential inventors. Take your own ideas a little further before giving them up. Keep your experience like a sort of treasure house that you can draw on whenever you like, but never, never let it be your master. Be on the lookout for impossible things, the sort the Red Queen dreamed up before breakfast. For example, in 3 dimensions, you know, we're not very good at thinking in 3 dimensions, we've said that before, but I've cut a hole in a piece of paper the size of a 5-penny piece. And I am now going to try and pass through that hole a 10-penny piece, which is obviously bigger than the hole. And I must not tear the paper in the process. How difficult is this? Well, really, it's not difficult at all, is it? Can you imagine what is the smallest diameter of hole in relation to the diameter of a 10-penny piece that I can pass through without tearing? There is a problem for you to worry about on the way home, and I think a profitable problem from the point of view of stretching your brains a little. So now let's go to 3 dimensions and see if we can repeat the trick. There are 2 cubes of the same size. I am going to pass one cube completely through the other. That ought to be good, doesn't it? But I first of all have to show you how much of this cube I have to cut away in order to do it, and what's more, in what direction I have to cut it in order to do it. Take out the wrapper and see the skeleton of the cube that's left inside is like that. It came out of there, you know it did, don't you? So you'll have no objection if now I push the white cube completely through the black one. That takes more making than you'd think. Now, Jacob's ladders. fascinating things, the standard sort of Christmas party trick. All the faces of that are red except the top one. We're going to send the top one on a journey down the back. Come on. Come at the bottom. Now, is that what really went on? Did that really? Let's see if we can send it back again then. Take it down. Send it forwards this time, see if it makes any difference. Come on. Is that really what's going on? Is the green one going from top to bottom? No. What is happening is that that one is turning over. That is kicking the next one back. That's kicking that one over. That's kicking the next one back, and that's kicking the bottom one over. You see, they all turn over. It is a game of odds and evens, and this one was just a trick. Thank you, Bill. Now, I used to think that Rudyard Kipling's poem If made too many demands on a man. These 4 lines, I think, are directed, aimed straight at the would-be inventor. If you can dream and not make dreams your master, if you can think and not make thought your aim, if you can meet with triumph and disaster and treat those 2 impostors just the same, you have to be that rugged to do inventing. You have to see your problem like the north face of the Eiger today, and when you've solved it, it crumbles into a little heap of dust so small you wonder how you caught your toe in it. Rudyard Kipling went on, if you can trust yourself when all men doubt you, but make allowance for their doubting too, I'm not sure I'm that good. Training people for invention is another game. Games are very good training for invention. Chess, of course, is very mind-stretching. Dominoes is said to be for old gentlemen in public houses. You have sets of things like this, and you have to put the 2 facing the 2 and a 4 at this end facing a 4. You can go at different angles if you wish, and they find that sufficiently brain-taxing. Now, if you play on a draft board so that the dominoes just fill the squares, you can ask yourself this interesting question. I've cut out the 2 corners, as you see. Before I did that, there was 8 by 8 pattern of squares, there are 64 squares. Now there are only 62. Suppose I gave you 31 dominoes, each of which will cover 2 squares. Could you cover those squares with 31 dominoes? You don't know? Well, you might have a try, and you might waste a lot of time. The question I'm asking is, can you prove that it can't be done? This is the sort of thinking that leads to an inventive mind. You say, well, look, the 2 I've cut out were both pink squares. So of the 62 that are left, 32 are white and only 30 are pink. One of these dominoes can only cover 1 pink and 1 white. So you can never do it. You'll always have 2 white squares left over. It's a proof. Now, extending the idea of dominoes, first of all, going backwards. That's a monomino. That's not very interesting, is it? Well, it can be made interesting. It can be made into 2-dimensional dominoes if you put spots on, because you can have to mate up a 1 with a 1, and then a 2 with a 2, and then a blank with a 1. That won't go. You can stick a 3 on the outside there, and you're playing 2-dimensional dominoes, which is more fascinating than ordinary straight line dominoes. And those were played with monominos. That's a domino. We've seen a domino. What about trominos? Well, trominos, there are 3 of them. That's not one. There are only 2 trominos. But you can have a variety of combinations of spot, can't you? My goodness, this is really 2-dimensional playing. And if you try and work out the number of possibilities of just putting the spots blank 1, 2, 3, or 4 on 2 pieces, one of 2 pieces that size and shape, you'll be amazed. You'll have a much bigger set of trominos than you did of dominoes, and the brain stretching will have gone a little further. If you go on to tetrominos, you find there are more of them. There's 1, 2, 3, and 4 tetrominos. Now, we don't put spots on these or it gets too complicated. The game gets, not worthwhile. And yet it's too simple with just the 4 shapes that there are, even though that has a left and right-handedness and so has that. These two are symmetrical in one sense. Let's just jump past those and go on to the pentominos, which are far more interesting. Pentominos are made up from 5 squares. And there are 12 of them. 12 different shapes, all made out of 5 squares. Those are all the possible shapes. Now, I'd like a member of my audience to come and I'll teach you to play tromino. Someone who's not been before. Yeah, can you climb over? Can you come to this side and then we can all see what you're doing? Now, all you have to do is to place a pentomino anywhere on the board. The object is to try to stop me from placing one on, and I shall try and stop you. So you can start where you like, any piece, any position. He might think that this is a random position that he makes, but it isn't. It's like chess. It has almost the complexity of chess. Now your turn. The idea is not so much to make patterns as to prevent them. That's rather clever. Not sure I'm going to win this one, Think very carefully. Yes. Yes, that's nice and clever. What have I got left? No. Not so. The problem's all yours. Isn't it? You give in? You will? Well, you shouldn't give in. There's one there, look. Thank you very much. Now, if you tire of that game, then all you've got to do is to separate these pieces into symmetrical and asymmetrical pieces. That looks asymmetric, but it isn't. It's just the same upside down as there as far as this game's concerned. So is that. This one's asymmetric. Turn them upside down. In fact, I've coloured the asymmetric ones a different colour on the back. The symmetric ones I've left white because there's no point in turning them over. Now we've got symmetrical ones and asymmetric ones, and now you can play these either way up. And that gives you yet another dimension. And now you can go on, of course, and do hexominos. That's when you get bored with this. And hexominos really get rather numerous. These are all the shapes you can make with 6 squares. They don't fit that board anymore. But you see how many there are. Why are they divided into piles like that? The answer is it's like cutting out the corner problem. Every hexomino in this set covers 3 pink squares and 3 yellow ones, 3 blacks and 3 whites. These cover 4 of one and 2 of the other. So these are the odd ones and these are the even ones. And rather than playing games, people have spent lots of time trying to put those together into interesting shapes, of which I've got an example here, showing clearly where the odd ones lie. And that is a difficult thing to do. That is simply an exercise in 2-dimensional topology. But a man who made it 3-dimensional produced this fantastic thing. He said, look, there are 12 pentominos, each made of 5 squares. 12 fives are 60. There are 6 sides on a cube. If you could put 10 squares on each side of a cube, you ought to be able to make all the 12 pentominos fit exactly around the cube if you make the side of the cube equal to root 10. So he stuck them together like that. If you examine that a moment, you'll see that it contains all the shapes I've got here. If I pick any shape at random, I can find it on this either one way up or the other. I'm having a job with this one. I know it works because I can't. Can you see it? Somebody come and point it out to me. On the side. Come on, you come and show. I can't see it from here. I'm standing too close to it. Where does that fit? That fits there. I think we've got a mistake on here somewhere. Anyway, the one thing that's not wrong is the outline. I think the two of these are alike, and there's a left and a right-handed one of those, and there shouldn't be, I think. Anyway, what he did was to turn it over and put the folds in at an angle to the lines of the pentominoes, an angle tan minus 1, 3. And then when he folded up the cube, the bits that were hanging over were filled in exactly by the holes in the other bits, so that by the time you'd folded it all round, you had in fact completely filled the cube. Now, imagine starting off to try to solve that without knowing whether or not it could be done. This is what amazes me about people who can do problems in topology like that. Let's go three-dimensional. Let's talk about monocubes and bicubes and tricubes. And straight away there are two kinds of tricube. That's one and that's the other. I mean, that's the same turned over. But when you go to tetracubes, there are all sorts of them. There's that one, and of course that one, and that one, and that one, left and right-handed ones. What else have we got? You mustn't put them skewed like that, doesn't count. That's the same as a square. Oh, let's have a look at the whole set, Bill. There's a left and a right-handed one of those. There's one of those, one of those, one of those, and one of those. What's this? That's not one of them, is it? You need this one to make a game. This also is sold commercially. The thing is that with 4 cubes in each, 6 fours are 24, to make a 3 by 3 by 3 cube, you need 27, so you put a tricube in. And then you try to put them together to make a cube. And we're so novicey at this that we daren't try and do it in public like this because we never get it right. You think you're doing all right until you get the last one. I'm in a mess now. So we got one made up beforehand so that you should see that it was possible. And I can take it apart and show you that there are the necessary pieces. And there is more than one way of putting the cube together. I don't know exactly how many, but it runs into teens, I think. There are a lot of ways, not including mirror reflections. But cubes are not the only thing you can make. You can make all these pretty things. There's an armchair, a settee, and an easy chair, a monolith or monument, a gravestone, and Mr. Coates here says that's a grave, but I think of it as a Roman swimming bath. And we've spotted them up to coincide with these so you can see exactly where each piece has got to fit. That one's going in there because it's got the same coloured spots. And then the question comes, can you really make all those? And if not, which one can't you make? It's like looking for the absence of pins, isn't it? It's a very difficult thing. This is actually the one you can't make. Because you look at the spots on the back, you'll find we left some off because you couldn't do it, even though it has 27 cubes in its makeup. So this is a great game. This also has been commercialised. Well, now I got my lads to produce me a very beautiful set. Before those, Bill, the transparent cube. I got them to build me a beautiful set of transparent cubes, all with spots on, and this is for 3-dimensional dominoes. You'll need one spot on each of these because the spots on the different faces are all different. And when you were starting a game, you'd start by putting one down, then you'd say, well, I want a red on that side. Have I got a red? Yes, I got a red there. Put that there. 2 yellows on the top. Gold. No. What's on the front? Green. All right. And straight away, you see, you'll be in a 3-dimensional game. And now they all have to fit on all sides. And that can while away many an hour. And when you're tired of that, you can play 3-dimensional noughts and crosses by dropping little coloured balls into some of the blocks and building those up so you can see where your moves were. But of course it would be rather expensive commercially, and the commercial version of these is shown here, where you have 4 decks and you have coloured counters, as it were, and you put them in, the reds and blues, and you make a move, and your opponent makes a move, and so on. And now there are a lot more ways of getting a row. A winning row can be 4 along there, which on our blackboard we show you how many possibilities there are of producing a row like that. Horizontal, parallel to the edge, as I've got it there, 32 possibilities. Diagonal in the horizontal plane. That's the usual noughts and crosses one, across the top. And there are 8 of those. Vertical parallel to an edge, there are 16 of those. That's a winning line too. And then diagonal in the vertical plane, of course, across there. That's a winning row. And finally, the most complex of all, right across the diagonal, 1 in and 1 across in each case, then 2 in and 2 across, and 3 in and 3 across like that, makes the most complex one. Now, did you notice you don't have a 3 by 3 matrix like you do for noughts and crosses? Why is that? Well, if you try it, you'll find that the one who starts can always win. So you have to make it more complicated. So you have to have a 4 by 4 by 4 matrix. Now, we think that we get confused with the 3rd dimension, the one that Einstein, the 4th dimension, or the one that Einstein meant. But really, a mathematician knows no boundaries as far as how many dimensions are concerned. He says, I can play 4-dimensional noughts and crosses very easily. Just want 4 of these. And now you've got some new kinds of rows you never even thought of. Because now this is to be regarded as a row. 1 in the first, 2 in the second, 3 in the third, 4 in the fourth. That constitutes a row. So does this. There are all manner of rows you can have now. The most complex of which is 1 in there, 1 in there, 1 in there, and 1 in there. That's the ultimate diagonal. But again, you'd find it too easy to win. So now you have to have a 5 by 5 thing and 5 decks and 5 of them. And that's playing in 4 dimensions. Well, why not play in 5 dimensions and have a 6 by 6, 6 decks of them, 6 rows and 6 rows this way. And then you can play in 6 dimensions and extend them down to 7s, and so you can keep building cubes on. And now you see how the mathematician knows no limit in his concept of n dimensions. We tend to think of dimensions somewhat differently, I know, as engineers, but the games are certainly very brain-stretching and thought-provoking. Now, let's go back and think a bit more fundamentally about ordinary things. How many spheres can you place in contact so that each one touches each other? The answer is only 4. You can't put a 5th one underneath because it wouldn't touch the top one. And yet we think of spheres as perfect. Let's try another shape. I think we'd better without the board this time. No, thank you. Let's try coins or big discs. I can actually put these 5 so that they're all in contact with each other. You start off with 2 on top of a 3rd one like that, and then you can just put the other 2 so that they touch the red one at the bottom, touch the sides of the others, and touch each other at the top. And there are 5 discs or 5 coins all in contact with each other. Well, is there another shape? Let's try cylinders, rods. How many of these do you think we could put in contact? 6, says somebody. All right. Well, to do 6, you stick them together like that, and you make another set with the opposite handedness. That's like that. And you manage to put one lot on top of the other. If they're long enough compared with their diameter, you can make them up to look like this. And if you then arrange those in exactly the right way, you can just get each one to touch each other by the time you get to the tip to make 6 rods all in contact with each other. And you walk away and say, clever boy am I. 4 spheres, 5 discs, 6 rods. 7 rods. You can put another down the middle. All those are in contact with each other. And the question I leave with you is there a better shape? Can you do 8? If so, what was the shape you began with? These are exercises for stretching the brain. Puzzles, conjuring tricks. This is a spring. Very ordinary thing. We've joined up the end so you can't cheat. We're going to drop a ring onto it so that we can just lift it off again. Would someone like to come and lift it off? Yeah, you can come on. Come round to the front, then we can all see. Come and lift the ring off the spring. How you doing? So look what you've done. You got it over 2 now. You see, the mistake you made was bringing it over the end. I know it looks ridiculous to bring it over the end, but look, all you've got to do is lift it off. Okay, now you lift it off. You'll all want to make one of these. Never mind, I'll show you. Look. A spring is, after all, only a straight piece of wire. You must be able to push it on and lift it off, mustn't you? Now, a little story about a mathematical postgraduate student called Arthur Stone, who was at Manchester University in 1939, and he got a fellowship to go to Princeton, and there he met up with some fellow mathematicians, notably a man named Tukey, a man named Feynman, and Bryant Tuckerman. And Arthur Stone found that his English binders for his notes were smaller than the American standard piece of paper. And so very laboriously he cut off all the strips about 1 inch wide from all his American paper. And he thought, what a waste of paper. So he started folding them. And he came up with such interesting things. He showed them to Tuckerman and Feynman and Tukey, and they formed a flexigation committee. They were the world's first flexigators, and here is a very simple flexigon. What you do with a flexigon is to open it out, and it's like a book. There's page 1, page 2, 3, and 4. Would someone like to come and find me page 5? Come on. By flexing, find me page 5. Stand this side and turn around that way, and you show me where page 5 is. You got it straight away, you see. Pull it open, don't be afraid. You've got to flex it. Pull the spline of the book apart. No, fold it up, and then pull. That's it. 5 and 6. Thank you very much. The only thing was, he forgot to look for 7 and 8. Every piece of paper's got 2 sides. That's a simple flexigon, but what about this? This is a hexaflexigon. That's orange coloured, and there are 3 patterns. There are diamonds, triangles, and circles. They make a hexagon, or a star, or a circle. What you do is to flex it about one corner and open it out like a flower, and you get another colour, another pattern. And then you do it again. And you get third colour, green. Now when you've got one colour, oh look on the back, you've got another. You've got diamonds in yellow now. Green, you've got circles. When you flex green, you've got hexagonal green there, and you've got orange on the front. And you can go on round doing this almost as long as you like, and it's a fascinating thing to do. Oh, look, we've got another colour. We got a red. What are we going to get now? Orange. It's a different one in the centre, but it's not really interesting. No, try again. We've had yellow. We've had green. Hey, what's this? Purple. That's 5 colours. Good grief. Yellow. Burn again. Actually, although I seem to be playing with this at random, I do actually know what I'm doing, because there's a 6th one. Now, what I was doing then was going through the motions in such a way as to bring up all the 6 colours and all the 6 patterns in the smallest number of moves. And that was invented by Tuckerman, and he named it a Tuckerman traverse. You now see there are 6 colours and 3 patterns. That is 18 possible combinations. But you can only get 15 of them. There are 3 combinations you can never get into the middle. They always stay as fragments on the outside. Now these are very bright fellas, and this was long before the Permissive Society. They made one with pictures on, so that when you got into the middle, you got the satisfaction of seeing the picture that you'd made up. And when you flex it, you get a different picture. Won't flex about that corner. What about that? Sorry. There's one. Nice picture of flowers. And when you get one of the rarer ones, they get to be more interesting, because on some of the... That won't open. 1, 2, here comes an interesting one. 3. Why is it interesting? Because it's got what the originator called pictures of comely, undraped young ladies in the corners. Ooh, I'd like to get that in the middle. Have another go. Of course, those are the 3 you can never get in the middle. And he therefore named it a hexasexafrustigan. Analogues again. Analogues. Think analogues all the time. It's all there is. It's your only sheet anchor for both research and invention. An ordinary child's pipe, as you might use for blowing bubbles, drilled right through to the bottom, and an endless belt of wool that's been joined to make an endless loop. Now, why does that interest me? Well, just because of the shape of the wool when I blow the pipe. The shape. Look at the top. See that little kink? It's always there. It seems impossible that the air from here could get up there. There's some very strange dynamics going on up there, and it's to do with gyroscopes, and it must have its counterpart in electromagnetism. And so it might just be fruitful to go looking for that kink in an equivalent electromagnetic system. Little kink, always there. Now, the search for a tidiness in pure science has probably been as hindering to progress as it was in the old alchemist days of everything made of earth, fire, air and water. That's all neat and tidy. We go home happy. Nothing is perfect, said the philosopher in James Stevens' The Crock of Gold. There are lumps in it. What a lovely description of the whole of science. When you think you've sewn it all up, there are lumps in it. When we dabble with left and right, with duals and parity and with mirrors, we become more conscious of human limitations than perhaps with any subject outside biology. We find a true humility that can be nothing but good. Mostly, I think we delude ourselves and create bigger problems than were ever arranged for us by nature. Let me quote you from a man who estimated the number of particles in the universe and found it to be less than a googol. A what? A googol. When I say a thing, say Humpty Dumpty, it means exactly what I mean it to say. And the man who invented a googol apparently asked his small son, he said, I've got a new number here, what's a good name for it? And his son said, a googol. And he said, that's it. Now, a googol is 10 to the power 100. Get a chalk. And Eddington estimated that there were only 10 to the 80-something particles in the universe. So 10 to the power 100 is 1 with 100 noughts written on it. Now the mathematicians wanted a bigger number still, a whole order of magnitude bigger. So they went to 10 to the power a googol. I'm not sure I spelled that right, but maybe AL, I'm not sure. But 10 to the power a googol, they called a googolplex. And if you notice, you can never write that down in decimal digits because you need more pieces of paper than there are particles in the universe. Said Eddington, however successful the theory of a four-dimensional world may be, it is difficult to ignore a voice inside us which whispers, at the back of your mind you know that a fourth dimension is all nonsense. I fancy that voice must often have had a busy time in the past history of physics. What nonsense to say this solid table here, on which Faraday as well as myself was leaning at one time, that this is a collection, said Eddington, of electrons moving with prodigious speed in empty spaces, which relatively to electronic dimensions are as wide as the empty spaces between the planets of the solar system. Looks solid to us. What nonsense to say that the thin air is trying to crush my body with a load of 14 pounds every square inch. What nonsense that that star cluster I can see in the sky now is a glimpse into the past age millions of years ago. Let us not be beguiled by this voice. It is discredited, says Eddington. We have found a strange footprint on the shores of the unknown. We have devised profound theories one after another to account for its origin. At last we have succeeded in reconstructing the creature that made the footprint, and lo, it is our own. We are the only monster. King Carnos, in the play Laughter of the Gods, says, a man is a small thing, and the night is very large and full of wonders. At the time we were doing our first experiments on the offset gyro, I was in the basement workshop below this theatre. Beside it, on a wall, is a huge portrait of Michael Faraday, who used to work here, and a copy of his own handwriting. Here's the picture that you see downstairs. There is a copy of the handwriting below it. As I'm doing this, Bill, we're running short of time. I wonder if you'd like to start setting up the gyro, and I'll read you what it says. Of this note here, it says, this note was made by Faraday on the 19th of March, 1849, when he set out in search of a connection between gravity and electricity and magnetism. We've been getting fairly near to that this week, haven't we? The final link of material forces in which he, that is Faraday, so firmly believed. He did not succeed in this quest, but the note expressed clearly the prime tenet of his scientific philosophy, which he followed with such outstanding success. This note reads, all this is a dream. Alice Through the Looking Glass was a dream. Still, examine it by a few experiments. Nothing is too wonderful to be true. If it be consistent with the laws of nature, and in such things as these, experiment is the best test of such consistency. We're going to do one more big experiment with the big gyro because we haven't done it before. I want you all to know how very, very much I am indebted to many people for the assistance I've had this week. From the BBC, without whose cameras we couldn't have shown you half the things, and all their staff, but especially to Bill Coates, Barry Owen, Cliff Johnson, and some of my boys who are doing research. Would you like to thank them in your own way? Have we not had too, with Alice Through the Looking Glass, a sort of dream in which at the same time we followed Faraday and tested it experiment by experiment? Did his quest really fail? I wonder. Let me send you away with this experiment and Faraday's words. All this is a dream. Nothing is too wonderful to be true. There are no words that I can add to better those.